Hello, my name is John Lynch. I'm a senior software engineer at Side Effects Software, and this is a masterclass on new Vellum constraint features in Houdini 18. So we've introduced several new features for constraints in Vellum for 18, and some of these are workflow enhancements, and these include things like automatically computing mass and thickness for your Vellum geometry based on density, which makes it much easier to work with geometry of differing resolutions. We've added the idea of normalizing stress computations over substeps, which is really just so that if you are doing stress-based fracturing effects, if you have to change the substeps, you shouldn't have to change those threshold values very much. We've introduced some new constraint features such as stiffness drop-off and tangent stiffness. We've added the ability to stitch Vellum geometry points to other pieces of Vellum geometry, but within the interior of a primitive rather than just point to point, which is how it had to work in previous versions of Houdini. We've added sliding for stitch and attached geometry constraints. And this is the idea where the target location on the target geometry that the constraint is attached to can actually move along the target geometry during the simulation and provide some interesting sliding effects. And then finally, we've introduced a new type of constraint called as rigid as possible, or ARAP constraints. And these are very useful for organic effects, simulating organic materials, and just general soft body, anything that needs to have good stretching behavior and good compression behavior. And these show up in both a triangle stretch and a tetrahedral stretch versions. So we'll go through what those look like and how they work. So the first workflow enhancement I wanted to go over is the automatic computation of mass and thickness for the Vellum geometry. So this becomes important because we want to reduce the resolution dependence of the simulation. So as you change resolution of your Vellum geometry, the behavior of the simulation shouldn't change all that much. And if you're working with something like infinitely stiff cloth, as you increase the mass, if it's infinitely stiff, the mass doesn't really make that much of a difference. But for something like bend behavior, how many wrinkles you get into your cloth, having much heavier cloth will actually bend fairly differently than very light cloth. So if you were trying to dial in a particular look for different resolution geometries, it could be sort of difficult. The other problem was that we had a default uniform thickness that we would use for all Vellum geometry. And if you fed in very high resolution geometry and started simulating, it would turn out that all of those points actually started out overlapping, which just caused some different types of problems with collisions in general. And so this is much more of a sort of fire and forget type setup. You can set up and not think too much about setting any of your thickness values. So the way it works is it will use the length of a polyline, the area of a triangle, or the volume of a tetrahedron, along with the idea of the density of the material to compute mass. And then as well, it will use the edge length to compute a thickness value so that the points won't overlap. Both of these values can be scaled by point attributes. So you can paint areas of higher thickness. You can compute it different ways. And we'll look at a quick example of doing that. So this auto computation is enabled for all Vellum tools in Houdini 18. So if you create cloth or hair or a tetrahedral soft body, for instance, all of those configure tools will be set up to use this auto computation. If you load in a previous file from 17.5 or 17.0, it will be set to the original previous setting of set uniform. So it will behave the same way it did before, but I would encourage you to use this auto computation in all your future setups and maybe even convert your old ones to that. So we're going to jump into Houdini and see how this works. So now we're going to talk about how to use the auto computation of mass and thickness in Houdini 18 for Vellum. This becomes actually pretty important in the context of cloth, which I'm not going to go into. We're going to have an entire masterclass on some of the new features that are very cloth specific for Houdini 18. So I'm going to show it actually in the context of this tree simulation here because it shows some different uses for it where it's still pretty valuable, I think. So this is a very simple setup. We've just created a default L system here, and it creates this little tree. If we middle click on it, we'll see that it's about 1 meter tall. If we look at the size, you can see that's about 0.97. So it's around 1 meter tall. So we're going to scale it up actually. But so to get started, we just create a little root point here, a little group that just encapsulates this bottom point here. And then we'll transform up the tree by scale it by 3 everywhere. So it's about a 3 meter tree now. And then we'll create some vellum hair out of it. And we'll set the thickness the bend stiffness very high. and simulate. And if we run this, we'll actually see that it does an okay job, but it's actually sort of falling over. So we're obviously not getting this extremely stiff bend stiffness that we were looking for. Part of this is just because we're not using enough constraint iterations. And so if all we wanted to do was keep these same values and get a stiffer simulation, we could just increase the substeps. And now when we play it, it's obviously slower, but we're getting much more constrained iterations per actual frame. So we get this much stiffer simulation. And that's fine as an option, but I think we should be able to do better. And so if we look at, let's start off by looking at what these parameters do, and the auto computation parameters, and we can start to get some ideas about what the issue is here. So what we're doing here, we're actually visualizing thickness. And this is a new feature in Houdini 18. So you can actually visualize the thickness on the Vellum Constraint node instead of having to go through the solver. So you can sort of change these parameters here and see the effect of the thickness immediately. So we've got the mass set to calculate varying, and we've got the thickness set to calculate uniform. So both of these options are new in Houdini 18. The Houdini 17 equivalent would be set uniform. This is how these things worked before. You would just set every point to a uniform mass and to a uniform thickness. So the visualizer is useful even in this context, so at least you can see before you start simulating whether there's any overlap. But generally, we want to use the calculate uniform and calculate varying. And so calculate varying means that each point will actually have a different value, and it'll have a different value based on a computation of its sort of immediate geometry. Calculate uniform means it will take some sort of average over the entire set of connected geometry and then apply that to each point. So let's look at the thickness first. And so what we're doing actually is looking at the edge length. So the length of the edge between each point, and then making a calculation based on that. So because of the calculate uniform, we're looking at the average edge length and then scaling it by 0.25 and then assigning that to the thickness everywhere. If we did this calculate varying, then we would actually see, and we set that to 1, you can sort of see here what this is doing. Basically, each point is just getting its kind of edge length to the next point. So all these thickness values, all these spheres will basically line up at 1. So we want to go back to like a quarter of that. So this gives it pretty good spacing to start off with. And actually, let's go back to calculate uniform. So as we run this simulation, we can also visualize the thickness here. So let's turn that on. So we're just seeing the same thing we just saw, but it's also got this nice extrude option that when working with polylines will actually draw little cylinders along it to actually let you visualize the thickness along the line. And if we hit play, we get kind of an idea of the problem, which is that we're simulating a tree, but the, in fact, mass of all of the branches up here are exactly the same as they are down at the bottom here in the trunk. Instead of having this big, thick trunk that's very strong and hot and dense and heavy mass, and then these lighter branches that are going to be supported by the constraints. So let's look at how we can use these computation values to fix that really quickly. So we're going to use this edge transport node. And edge transport, it does some kind of interesting things where it can calculate things like distance along a network of edges, which is what this is. So we've got this set to edge network, and we're just basically going to be calculating a distance value along these edges, starting from that root point that we started down here. So because what we're going to do is we're going to calculate the distance from the root to all of these points up here, and then use that to create a variable density value that's going to make us specify that the lower points down here at the trunk are much denser than the ones that are up top here. So if we visualize this, actually I don't think we have a visualizer, so we'll add a visualizer real quick on the distance parameter. I mean the distance attribute that we created. So you can see that it starts out blue, so it's 0 down here, and it gets higher as we go up. And in fact, we can, if we change that to a marker, we can see the value. So it starts at 0 at the root, and then we're just measuring the distance along each branch. And so as we go up to here, we get up to around 1 meter. So we're going to actually create a density value. This is a very simple thing. We're just going to create the density, and we're going to map that 0 to 1, because it starts out at 0 down here and goes up to about 1. And we're going to say, well, the density at the root's 0.1, and the density, and these are kind of made up numbers because we can scale them later as we want to in the Vellum constraint. But the important thing is that it's quite high at the root, and then at the branches, it's quite low. And then if we go into our Vellum hair, let's turn the visualizer off. Then when we say calculate varying, actually, let's switch over here. And so now we're going to actually be scaling by this density attribute. Before, the density attribute didn't exist, so it's just created and treated like one. But now we're actually scaling by the density attribute. And then if we go to our Vellum solver and hit play, you'll see that all of a sudden we have this fairly stiff simulation because we basically got these high mass values down here and these much lower mass branches up here. We still got the same thickness everywhere, which looks a little bit weird. So in this case, let's go ahead and change our thickness to calculate varying. And we're going to scale by an attribute. We'll actually go ahead and use that same density attribute. And you could use a different attribute. In fact, it defaults to a thickness. But we're going to go ahead and use density just for convenience. So we're going to have to scale this way up. You can see we have these tiny little points. If we and everything is extremely narrow here, so we want to scale this up. And so as we scale it up, you can actually see we've kind of got this nice thick trunk here, and the branches are very narrow. And it's going to look pretty much the same because there's not too many collisions going on. But if we do things like make a forest out of this and maybe remove the pin at the bottom. Right now we're pinning the root, but we'll let them sort of all fall over. Play. And we'll just see that as the collisions start to happen, again, you've got these, and not a lot of collisions happen in this case, but you've got these thick, heavy mass trunks down here, and then these much lighter, thinner branches up here that are all interacting in a sort of more believable way than if they've just been these all big, thick branches, or all uniform thickness through the entire extent of the tree. So this is just a quick example of how you can use those computation values to kind of have more control over any sort of simulation where you've got geometry that's varying in thickness or in mass along it. And in the cloth masterclass, you'll see examples of using differing resolutions for doing some of the same types of effects. The next workflow related feature I wanted to go over is normalizing stress computations. And this is important mostly in the context of breaking or tearing cloth based on something like stress threshold. So we can now normalize these computations over time, which just means if you need to change the substeps for some reason, if you, for instance, introduce some very fast moving collision geometry and need to increase the substeps, you shouldn't have to change the values you're using for those thresholds very much relative to the previous versions of Houdini. This also works well in conjunction with density computed mass. So what we were talking about just before, if you've got cloth that has a consistent density, but you're changing the resolutions, the stress values should still be fairly consistent. So it just makes it easier to set up values that will work across a wide range of time steps and resolutions. So it's enabled by default in Houdini 18, similar to the auto computation, but will be off for any versions previous to that, just so that you get similar behavior from your old files. But again, in future setups, you should probably always use the normalize stress option on. So it's just a kind of a convenience feature, and I'll just real quickly walk through how it works. So this file is just a really simple example of cloth tearing. We've got a planar patch here that sets up the cloth, and then we've drawn a curve across that cloth and used edge fracture just to separate it into pieces. Yeah, so you can see the two pieces here that we fractured the cloth into. Then we turn it into cloth and we weld it back together again. So a very basic tearing setup. And we're pinning this corner up here. And we've got a low breaking threshold for stress here. The type of breaking is stretch stress. And then in the solver, we're actually visualizing that stretch stress. And actually, let's view our welds and our pin to target as well. So if we hit play here, we'll see the stress values kind of starting up here in where you'd expect up near the pin. And then it starts to tear, and then the stress kind of propagates along the tear here. You sort of see as they get red, basically these welds start to break. And so we've actually tied this visualization here to the same value as the weld breaking. So again, just a very, very basic setup for tearing. The problem is that if you then went to the Vellum solver, and I should be clear, under advanced, so now all of these, what these used to be folders, and now they're collapsible drop downs. So under the motion one, we have this normalized stress, which again in 18 defaults to on, but if this were a file brought in from a previous version of Houdini, it would be turned off. So it's off here. And if for some reason, let's say we had to move up to 3 substeps for some reason, new fast collision geometry, something like that, and hit play, you can see the stress values are completely different. The ones that are being computed by the solver for all of these stretch constraints in the cloth, they're getting very different values. And so basically our tearing doesn't work anymore. So we would actually have to go in and change these values fairly significantly, these threshold values fairly significantly, to get some sort of similar behavior. So if we go over here, we've got a pretty similar setup. Let me turn that visualization on real quick. So we want weld and pin to target. And we're getting a similar tear at one substep. And you'll notice that the values we're using are quite different. And that's because these values are being normalized over time. So this is why the normalized stress is not on by default, because you have to change all these values. So we're using a different value here for the tearing. But what's nice is that because on the solver, on the advanced tab, we've got this default normalized stress on. If we say move to 3 substeps, you'll see the stress values are fairly similar. You're not going to get the exact same tear just because you're doing more substeps here, and so things are going to look a little bit different. So you might have to go from, say, that seems to tear faster, so you might have to go from, say, 0.055 to like 0.06, for example. But it's a very small change. I mean, the values in that same sort of ballpark should generally work. And then just to demonstrate that this holds up pretty well with different resolutions, if we, let's say, switch to a lower resolution cloth, we'll still have a similar fracture across here because we're just using it based on this curve. If we change, we need to change the pin point real quick because the point numbers have changed. And then, actually, let's go back to one substep. You see the stress values are around the same. So the tear works fairly similarly, and that's partly because we've got this the defaults for the auto computation of mass here, so that the overall mass of the piece of cloth is staying the same even as we change resolutions, and so the fracture or the tear is working fairly similar both across these different resolutions and across the different number of substeps. So that's the value of the normalized stress option. Now we want to move on to new features of constraints that we introduced in Houdini 18. And the first one to talk about is stiffness drop-off. And so this is the idea that you can actually have a stretch or bend constraint reduce or increase its stiffness as the constraint moves away from the rest state. So that would mean for a stretch constraint, as it moves further away from its initial rest length, so let's say it's a pin, as it moves farther away from the pin, it can actually fall off in stiffness or increase in stiffness. So it can, say, start at a very high stiffness or medium stiffness, and as it stretches, it'll actually get weaker over time if it's reducing. You can also use it with a bend constraint, so you could do something like have a bend constraint start off very weak and then increase as it moves away in degrees from its initial orientation to get stiffer over time. And both of these can be sort of interesting effects. This feature was actually introduced in Houdini 17.5, but we've never demonstrated it before. So I just wanted to give a quick demo of using it in the context of a stretch constraint. So let's move into Houdini and see how that works. So let's look at using stiffness drop-off with stretch constraints. So we've got a simple setup here where we've got a grid that we're applying some attribute noise to. We're creating this pin scale attribute that's just using noise mapping from 0.1 to 1. I think we've already got a visualizer on that, so let's look at that. So the areas that are red will be very stiff, and the areas that are blue will be less stiff. And then we're creating cloth from that grid and pinning all of the points. So we're pinning every single point, and then we're scaling the stiffness of those pins. They're actually they're soft pins, and we're scaling its stiffness by that pin scale attribute we created. So if we solve this and we're visualizing those pin constraints on the visualize side by stretch distance, and so we hit play, we can actually see those blue areas where it's weak, it sort of stretches a lot from the original pin position, and the red areas it's staying much closer to the original position. So what we can do is we can, so we're looking at the stretch distance here. And so these are stretching maybe, then stretch distance is always in terms of length. So this is 0.2 meters. So this looks like they're maybe stretching about half that. And what we can do here is actually go to the pin, and we're going to turn on that stiffness drop off for the stretch constraint. And so what's going to happen, actually, let's turn this off for the moment. What's going to happen is as these pins stretch, they're actually getting weaker. So we've got a stiffness drop off, and it's decreasing. So as it gets closer and closer to 0.2 meters of stretch, it's falling off to 0, the stiffness is. So you can see we're visualizing stretch distance here. As they get closer and closer to that 0.205, they're starting to get closer and closer to turning red. By the time they turn red, they are actually down to 0 stiffness. So as this stretch distance approaches this value, the stiffness gets weaker and weaker because it's such a decreasing, and it gets to 0 as it reaches that full stretch. And so basically we've got a bunch of constraints. All these constraints aren't doing anything, and you get this kind of soft release effect of the cloth from the pins. Just sort of releases it gently sort of onto the ground. Now, the other thing we can do is, since these constraints aren't doing anything, these are all zero, effectively having 0 stiffness, we can actually make them breakable and use that same threshold. So we're gonna make these pins breakable by the same stretch distance that we're using. So when they get to 0 effective stretch stiffness, because of that drop off, we're going to just go ahead and break them. It'll look pretty much exactly the same, but you'll see these constraints actually go away as we reach the same that drop off point. So again, you get this kind of soft release of the constraints. So it just sort of fairly gently puts the cloth down because the stiffness has dropped off to 0. So that's just a very simple example of using the stiffness drop off. Remember, it's always in terms of distance. So in the case of a length constraint or a stretch constraint, it'll be length, it'll be meters, and in the case of a bend constraint, it'll be degrees. So that is stiffness drop off. The next constraint feature I wanted to talk about is tangent stiffness. So that's the idea of, once you've constrained, say, cloth to a character's waist, for example, you want to constrain any movement of that cloth in the direction tangent to that target geometry. So you don't want the cloth to slide up or down away from that original attachment location. So it just does a better job of holding cloth in place without sort of falling down or rising up. It only works on attached to geometry constraints. So when you're attaching vellum geometry to external geometry, you very often and usually the collision geometry. So for example, like the cloth to a character body, it works in conjunction with sliding, which we're going to talk about soon. It sort of fights with sliding as well in a lot of circumstances. So we'll also look at how that happens. And it's worth knowing that this actually adds another constraint primitive when you turn on tangent stiffness. And it's mostly worth knowing that just if you're doing something advanced like braking or something like that. But in any event, let's look at a quick example of how you can set this up and how it works. So let's see an example of using tangent stiffness to hold up a piece of cloth better on its collision geometry. So here we've got this sort of something like a skirt that we've subdivided just to get some more resolution. And then there's another tube that's going to be on the inside that's going to act as sort of our character body. And we are attaching the skirt to the body. So this is just using the attached to geometry type, and we're doing it for this edge that's around the top of the skirt here. So fairly simple. If we solve this, we've got all these distance constraints here that have a rest length of the original distance from the skirt to the body. And so if we hit play, you'll see that the first thing it does is it falls down. So it's maintaining the distance of the points on the skirt to the body. The problem is that it's because that original distance there was actually a fair bit of a gap there. That distance, then it just, as the skirt falls down, it can maintain that distance, but the skirt is moving in the tangent direction, like basically falling down vertically as soon as the simulation starts. So even though the constraints are being satisfied, it's really not probably what we want. It's not a particularly good look. So what you might do previous to Houdini 18 is you might say, okay, well, either use different collision geometry that maybe is expanded outwards or something like that. Or you can do something like say, okay, well, let's just change the rest length scale. So maybe I'll change that to 0.25. And so what it's going to do is it's going to basically decrease the length of all of these constraints and sort of suck in the skirt around the waist, as you see here. So that's not a terrible solution, but it also changes the look of the skirt. Now you've got this sort of, all these springs or these distance constraints are actually much closer. And so it's kind of created all these wrinkles and kind of folds in the skirt that you may or may not actually want to be there. So what tangent stiffness is designed to do is actually let you say, well, with this particular set of stiffness here, I want to actually keep the skirt constrained in the tangent direction of the collision geometry. So if I hit play, you'll see what it does. It basically has another constraint applied that holds it in place in the tangent direction. So it's maintaining the distance away from the waist, but it's also maintaining its distance away from this normal, basically, out from the waist here. So the shape of the skirt stays much closer to how it was originally, and it stays in the same vertical location as well. And if you decrease this a lot, like say put this to say 10 or something like that, you'll actually see there's actually, for the visualization, this first top sphere, maybe decrease it further to 1. Yeah, this first top sphere is the normal location, and then this is giving another indication of how far it's dropped away from that normal location. So this is how much it's moved in the tangent direction. And normally, obviously, you probably don't want a lot of that movement. So we'll set it higher and just get a tiny bit of movement there. And you can obviously make that even stiffer if you wanted to. So the one thing that's also worth knowing is if we visualize the attached constraints that are coming out of here. So we've created a group here, and we're looking at the constraint geometry. And let's look at the type. So normally, there's just a bunch of these strong attached constraints that we've created with this almost infinite stiffness. But if we enable tangent stiffness, we actually get a whole bunch of new, or well, actually the exact same number of new constraint primitives that are these attached normal constraints. So what it's actually doing with this stiffness that we're setting here. So it's actually doing is having another constraint that's setting a distance to this normal from any attachment point. And they will have actually, if we look at the target values, they'll actually have the same target values. They'll be pointing to the original target geometry, which again, in most cases is the collision geometry. So just like the attached constraints, these attached normal constraints will be pointing at a particular location on a primitive, but then it'll be using the normal out there to try to basically stay constrained to that normal. So that's what tangent stiffness does. It actually creates these separate set of constraints that will constrain the location to the normal as well. We've also made some enhancements to the stitch constraints in Houdini 18, which, just as a reminder, are distance constraints between pieces of vellum geometry. And before Houdini 18, that could only be point to point. So you could constrain one point on a piece of cloth to another point on either the same or a different piece of cloth. But you couldn't, for example, constrain that point to the middle of a quadrilateral on that cloth, which just ended up being fairly limiting when you were trying to, say, attach a pocket or something to the middle of a shirt. So in Houdini 18, that point can now be constrained to the closest location on a primitive. So, for example, the middle of a quadrilateral. That target primitive can be a polyline, a triangle, or a quadrilateral. It actually, when you enable this, it actually creates a different constraint type called a point prim constraint, which you don't really need to know. You'll never see it unless you're actually looking at the output of the Vellum constraint SOP. The UVs are stored in the rest vector so that they can be used in the constraint solve. And then this is not really a stitch enhancement, but the attached to geometry constraints, which again, remember, are Vellum geometry to external geometry like collision geometry. Those can now target polylines as well, which is new to Houdini 18. So we'll see an example of that when we talk about sliding, actually. But for now, let's look at an example of the new stitch enhancements. So another very simple example here, we've got a hanging piece of cloth we're calling a shirt, and we've got a smaller piece of cloth here we're calling a pocket. And we're just going to stitch this pocket to the shirt. So here we've got this use closest location on primitive off. This is how this would have to be set up in anything before Houdini 18, because this option wasn't even available on stitch constraints. So if we hit play, as you'd expect, these points here on this pocket cloth are constrained to the nearest point on the larger piece of cloth. And, it's staying in place. It's kind of okay, but if anything sort of pulled on this cloth, it would start to become extremely obvious that everything was attached to these points, and you get these weird situations where like these 2 points are connected to this particular single point, whereas all the other ones only get connected to one point. So it's just a little bit of an unwieldy situation. And if you did something like, well, I want to I want to make them, closer to their pin location. So I'm going to decrease the rest length scale to say 0.5. You start to see these, as soon as you do that, you realize that you've got this kind of long distance constraint that's really creating a lot of pulling and wrinkling that's kind of unpleasant in this setup. So with Houdini 18, you can now turn on this use closest location on primitive, which is an option that's been for the attached to geometry constraint available, but now it's available for stitch constraints. And now you can see we're stitching these particular points to the interior of these target primitives. And so you just get kind of a much nicer sort of consistent setup here where all of these points can actually go to truly the closest location on the target geometry. And if you do something like, decrease the rest length of it, it really makes no difference because all it's doing is making it come a little bit closer to that already very close point. And as I described, it actually is creating a different constraint type here. So if we turn that off, we get what you'd expect, which is a stitch constraint with a rest length. And if we turn it on, we get a slightly different constraint type. And we're actually storing the UVs here in this rest vector. You still have the rest length, but you also have, but the location is specified by with these UVs stored in the rest vector, the location on the primitive. And then the other thing to see is that this actually works with polylines as well. So if we switch to where our target geometry is going to be this line here, this piece of string, and it's the same sort of situation where if we hit play, it generally works okay. We've got cloth constrained to the string, but again, we've got, each a couple of these target points have two constraints going to them. One of them has one. It's just kind of unwieldy. And again, if we do anything like decrease the rest length, things just get very ugly quickly. So again, we can use closest location, and these constraints will actually be so close to points, but these are just sort of in the middle of these line segments here. And if we hit play, we could just get a much nicer, smoother simulation, and we can do things like decrease the rest length scale, and it just looks fine because all we're doing is making these points go closer to the location on the polyline itself. So this just can be really useful with stitching in general. It also makes sliding available or possible because we can slide along the interior of stitched primitives, and so we're actually going to see some examples of that next. The next new constraint feature I want to talk about is sliding constraints, or at least that's how they were referred to in the launch video for Houdini 18, if you happen to see that. And this is the idea that if you've got stitch or attach constraints, they've got an initial target position that the point is constrained to. And with sliding enabled, that position can actually slide along the target geometry. In the launch video, this was described as a new type of constraint. We've looked at some new constraint types in this masterclass so far. This is actually not a new constraint type. It's really just a new feature of the stitch and attach constraints. Essentially, you enable some parameters which create some new attributes on the constraint primitives, and that acts as a signal to the solver to try to slide the target point along the target geometry during the simulation. So that primary parameter is just called sliding rate, which controls the speed of sliding. It can actually be scaled by attributes at simulation time. So this is different than most of the attribute scaling that we've seen so far in Vellum Constraint. In this case, sort of the whole point of sliding is that the points that are involved in the constraint are going to change over time. So we actually need to be able to look up those attribute values at simulation time. So there's some extra information that's stored on the constraint primitives that allows us to do this. And allows some pretty interesting effects that way. There's two different methods for sliding the point along the target geometry. Basically, at each time step, we need to figure out sort of the next best candidate location on the target geometry. So the easiest and quickest but simplest is just to find the next closest point. And that's fast, but it can skip over gaps. So if you've got concavities in your geometry or someplace where two pieces of geometry meet, like where the arm might meet the body of a character, it can sometimes skip over gaps because the next closest point is on sort of non-connected target geometry. And I'll show you an example of that. And the other method is what's called traverse polygons, which actually walks outwards from the current sliding position to the next one along the connected polygons. And it's slower, but since it's using connectivity, it does a better job of not making jumps over gaps. And again, I'll show you an example of that. It is worth noting that if you're using tangent stiffness, that it actually, the sliding constraints can sometimes fight against them when you're operating under gravity, or where the sliding direction is as a result of gravity, and where the sliding direction is also tangent to the collision geometry, which happens a lot. So I'll show you an example of that. And you can also, of course, create these dynamically and give something like sliding collisions. So if you've seen the Advanced Vellum Workflows Masterclass, we looked at how to do sort of sticky collisions where objects would collide with geometry and get temporary attached constraints that would break. And then over time, they would rejoin as the object sort of stickily rolled down the collision object. This is different, where you want to just create one sliding constraint when the object collides with the target geometry, and then just have it slide down that collision geometry. So we'll look at an example of that also. Now let's look at this file that has a bunch of examples of sliding, attach, and stitch constraints. And let's go through each one of these examples and just sort of see how you set up the sliding in the first place, and also how it's represented on the stitch and attach constraint primitives themselves, because it can be pretty interesting and also useful for debugging, or if you ever want to create some of these constraint types yourself manually, not through Vellum constraints, then it's useful to know what attributes are involved. So this is a simple example where we've just got two lines, both set up as strings, and we are stitching the bottom one to the top. And if we hit play, we'll see it just sort of slides along the top string. So these are stitch constraints. These are the stitching to polyline constraints that we were talking about that are new in 18. And if we actually look at what's being created here, so here's the Vellum constraints that's creating the stitch. And if we look at the attributes, we've got the rest length, which is the length of these initial distance constraints here. And then we've also got these rest vector values that represent the UVs within each line segment. And these are actually what are going to be updated as it slides along. The sliding rate here tells it how fast to slide. So if we turn this off right here, that attribute goes away. And if we hit play, then it just doesn't move. So this is just a standard stitch constraint. So really the only difference is that attribute, which tells it how fast or how quickly to try to move these target points along the target geometry. So if we actually look at, so this is looking at the Vellum, the constraint geometry coming out of the Vellum constraint stop. If we actually look at the constraint geometry as it comes out of the solver itself, so this is what looking what the solver is doing with these constraints, and hit play, we'll see that the first component of this rest vector, because it's only a one-dimensional thing, this is the U along each polyline here, the U of the UV, but because it's one-dimensional, we only need one of them. And it's what gets updated as it slides along. So these are all changing because it's sliding these along the polyline. But the other thing that's changing, if you notice, this points array here is the point numbers that are involved in each constraint. This is normally an internal attribute that you don't really need to save or look at or anything like that, but it can be useful for debugging. If we turn on our point numbers, we can see that like this bottom constraint here corresponds to point number 32, and it's constrained to the line segment between 8 and 9. And as it slides, now it's going to change. It's now corresponds to the line segment between 7 and 8. And so both of these are being updated. So now it's 32 and 5 and 6. It's between this line segment. So that's what the solver is doing, is internally is updating the line segments it's attached to, and also this U value. And the fact that the points are changing just tells you that actually the topology of the constraints is actually changing. This particular constraint, the points that are involved in it are changing as it moves between these line segments. And if you remember, if you watch the Advanced Vellum Workflow class, you'll realize that means that we need to basically regraph color, repartition the constraints before we send them to the GPU, because the topology is changing. So that's just something to be aware of. If you see your simulation graph coloring a lot and you're wondering why, and you've got sliding enabled or sliding between pieces of Vellum geometry, this is why, because the topology is changing. And there's unfortunately just sort of a necessary cost with doing this kind of operation. So if we create a sliding scale attribute on the target geometry, so that's what we're doing here, is we're just creating basically a fall off here. So we're basically going from, this is all 1 to 0 over here. So this is an attribute on the target geometry. And then when we set up our stitch, we can say, let's scale by attribute. And it's going to use that sliding scale attribute. and it's going to, for a promotion method, is going to use target. So all that means is it's going to use the attribute values that are on this target geometry and not try to blend in any of these at all. Not like an average, for instance, would use these 0 values. So this just avoids having to set that attribute on both pieces of geometry. If you just want to set it on the target, which is generally for sliding probably the most useful, then you can just set it here. So now if we hit play, play on the actual with the solver visible, it will slide freely into that section where it has a sliding scale of 0, and then it'll actually get stuck. This one down here will get stuck, and this one can still sort of slide around. So if we look at what's being written out to those attribute primitives, it's actually saving not only the sliding rate, but it's actually keeping track of this attribute name here, this sliding scale, and the attribute promotion mode. And the reason for that is normally when you do it like a scale by attribute, in the constraint operation here, and when it's creating the constraints, it looks up those attribute values, scales the stiffness or sliding rate or whatever, and then ignores it from then on out. So it doesn't look at the values of the geometry anymore. It just sets those values at the time of constraint creation. But because for sliding, you're constantly changing the points that are involved in the constraints, as we just talked about, you need to be able to look up those values at simulation time. So it actually has to save the name of the attribute and save the promotion method as well. So this is basically a way of having it dynamically update based on these values in the target geometry. So this is also here just a quick demo of sliding along a polyline. So again, we just got the similar line here, but the target now is actually external geometry that we've created, just this very finely subdivided line that is not being simulated. This is just sort of static geometry that we're attaching to. So here, the same thing, we just sort of set the sliding rate on the attached to geometry constraint, and when we hit play, it'll just slide along here. So this is this string down here, this is the Vellum geometry, and this is external geometry. It's just sort of sliding along. And you can do the same thing with attributes and stuff to control how fast it slides. So for things like a curtain that needs to move along a curtain rod or something like that, these types of constraints along polylines are really useful, sliding constraints along polylines. And this is all new to Houdini 18. So now this is an example of a couple of tetrahedral soft bodies being stitched together. And both of these are using this tetrahedral stretch constraint type that is new in 18, and that we're going to be talking a lot about in just a second. But so if we look at this setup, there's a few things going on here. So we're constraining from the points on this piece of geometry here is being constrained to this piece of geometry that's being stitched to it. And then there's some pins up at the top here. If we hit play, the other thing we've done is we painted that sliding scale on here. So instead of doing it like as a drop-off, we've actually used this attribute paint here just to paint sort of a low sliding speed here and a 1 sliding rate here. So that's kind of what you're seeing here is that if we play it back, the stitches move kind of slowly along here, but then very, very quickly down this side. And that's why this constrained object kind of tilts as it goes down. It's because it's going slower on the right-hand side and faster on the left-hand side. And then you can see that the location of the stitches is kind of moving along the target geometry, sliding along the target geometry. And so we've got this gap here, and we've actually got the Vellum solver. So we're on the advanced tab under motion. We've got the sliding method here, and we set it to closest point. So it's actually doing a pretty good job of not jumping this gap here. And the reason for that is because this sliding rate is painted so low that it basically is sort of projecting along these constraints to figure out where the next location should be. And because it's a fairly slow sliding rate, it's maybe only projecting maybe down this far, kind of this, not too far down the actual constraint. And so when it tries to find the closest point, it's actually going back up to this top piece of geometry, which means it's doing a pretty good job here. So we might be normally worried that it would just kind of jump this gap, which would look kind of strange if we're really tracking the target properly. but it's staying in the right position because it's a slow sliding rate. So a lot of times you can use this closest point if you don't have any concave geometry. Clearly we do have some in this case, or you're using a pretty slow sliding rate. If, however, we go back to the stitch and let's just turn off the scaling altogether, and we'll see that it goes now equally fast, and then it actually does skip that gap. So we're not getting that rotation anymore of the constraint. It's all going at the same speed. And then because it's sliding at a very fast rate, once these constraints get down here, they're sort of projecting back very close to these points, the original points, the constraint points, and they're skipping down. They're jumping this gap down to this lower level here, which, depending on the look you're going for, the effect you're going for, may or may not be acceptable. So this is where this, or situations like this, is where this traverse polygons method can come in handy, because in a case like this, it will actually make sure that it doesn't skip that gap. What it's going to be doing is traversing all of these triangles here on the surface, looking for a way to get closer to the constrained point as it slides, because it can't, because everywhere it has to go is farther away. It won't ever jump down to this gap. So you'll actually get it staying sort of where it should have been in terms of connectivity. It's a bit slower, especially at high res. We're actually looking at some methods for speeding that up, maybe optimized just for triangles. So I guess my general recommendation is start out with the closest points, which is the default. If you start seeing some jumping between gaps that you don't like, try this traverse polygon setting instead. And then the other sort of important thing to realize about this setting is that when we do this solid conform here, this is on the target geometry, this geometry here, we're doing this add surface triangles. We're leaving that checked on. And that's so that we have a set of triangles on top of the tetrahedra that make up this soft body. And the reason for that is that the target of a stitch constraint, like we talked about before, can be a polyline, a triangle, or a quad, but it can't be a tetrahedron. It needs to be one of those first three types of primitives. So we actually are just keeping a bunch of surface triangles here as well, which don't really cost that much. We don't have any constraints on them. They just exist as primitives, basically. And then when we create those stitch constraints, the target group is those surface triangles. So it is actually being constrained to the triangles themselves. So finally, this is another one where we're going to look at the effective tangent strength and tangent stiffness that tangent stiffness that we talked about before. So here we've got external geometry. So we're using an attached to geometry constraint. So we're just attaching this again, tetrahedral soft body to this external object. And it's painted again. So everywhere it's red, it's going to slide quickly. And everywhere that it's blue, it's going to slide slowly. So we again get this kind of leaning or rotating, because we've got slow areas here and fast areas here. And so it slides down. And by the time it gets to the bottom, it'll essentially stop. So actually, let me show you one thing really quickly. So if I'm sliding along and I actually want to just stop it completely, the fastest or the easiest way to do that is use a Vellum constraint property. And there's now a sliding rate property within that. And we just apply it to the attached group. And here we're just saying, okay, if it's after frame 20, set the sliding rate to 0. And setting a sliding rate to 0 just effectively stops all sliding. So in this case, it'll slide for 20 frames, maybe easier to see from this side, and then just stop altogether. So turn that off again. And then, so if we look at these attached constraints, they have got a tangent stiffness set. So for now, let's turn off our scale by attribute. So we're going to let this slide as fast as it can and uniformly. And so as it slides down, we notice that it gets to the bottom of the object at around, say, frame 40. So around frame 40 or so, it's kind of down to the bottom of the target object here. Now, if we go and turn off our tangent stiffness and hit play, we'll see that it actually slides much faster. It reaches the bottom, more than twice as fast, like around frame 18. And the reason for that is that the sliding and the tangent and the constraint solving are done at separate times within the solver. So if you've got the tangent stiffness on, these constraints here, the ones we talked about earlier, are sort of trying to lift the constrained object up, where at the same time, the sliding is trying to let it go down, essentially let it go down according to gravity, whereas the tangent stiffness is trying to keep it up. So they're basically fighting each other. So that's why it's slower, is because you've got the sliding going on and the constraint solve happening, which is trying to keep it up, and they're in complete disagreement. So it still works, but it just means that you have to be a little careful about adjusting like your sliding rate here at 0.75. So you could get it a little faster by going all the way up to 1. Also, decreasing this tangent stiffness will make a difference. So if you decrease it so that it's fairly light, you'll see that it goes faster again, because it's actually the stiffness is low enough that now it's actually letting the object fall some. So that's another option, is just decreasing the tangent stiffness. So in any event, it will work. You just need to be a little bit careful about how you balance these two forces, or these two constraints, and sliding together. And then finally, this is just a quick example to show that this stitching between pieces of vellum geometry works across sort of different primitive types and across welds. So again, we've got two pieces of vellum geometry. This one starts as triangles, turns into quads, and then is welded across to strings, and this constrained piece of geometry slides across all of them. So this is just showing that not only can the points that are involved in the stitch constraints change, the number of points involved can change. And so that this, again, the topology is changing, so we're having to update the graph coloring and repartition, but it just is showing that it's capable of doing that. And then if you do something, so this actually even means that things like breaking and stuff work. So if we go to the welds, so these are the welds that are holding these strings onto the bottom of this cloth, and we go and turn on breaking, the constrained cloth can actually slide down the target cloth, cross over the welds, and then at some point there, as they get towards the bottom, they'll actually create enough stress that it'll break the welds, and you can get sort of a fracturing effect. So anyway, this is the sliding. Most of the examples, I'm going to show you a quick example of using the sliding constraints, but in a dynamic setting, so where you're creating them at simulation time. So we'll look at another file to do that. And very quickly, I just wanted to demonstrate using these sliding features in a dynamic constraint situation. So this is a file that's very similar to one that was in the Advanced Vellum Workflow Masterclass I referenced earlier. And in fact, if we look at that version, this is what comes out of that version. And what we're doing here is actually using non-sliding constraints, but making them breakable. So we get these kind of sticky collisions. So these constraints keep sort of breaking and reforming as the object sort of slides down, as it kind of bounces down the wall. And then there's also some glue constraints between the objects themselves, which we're not showing in this new setup. But you can see this is basically kind of a sticky collision sort of look, kind of a stiction type look. But it's the same idea of dynamically creating the constraints whenever they get close enough to the collision object. So what we're doing here is a similar setup, but we've created some noisy sliding scale attribute again on our target grid, our collision grid. And if we hit play, actually, and so I'm just kind of merging all the visualizations and the grid and all these things together at the bottom so we can see them all at once. So you'll see that the attached constraints are created dynamically, but then they just slide. And they're again picking up the sliding scale from the target geometry here and sliding along. And so depending on, it's faster without the visualization. So you can sort of see like this object starts out fast and then it slows down the sliding as it kind of gets to this blue section, which is the low sliding scale. And then like as this object gets to the red part again, or the high sliding scale, it sort of speeds up. So just kind of a different look, a different type of sliding collision. And the setup for it is very simple. Vellum constraints dot here. And the type is attached to geometry. It's creating the constraints each frame. And it's doing it only within the max distance of 0.1 here. So you can see them being created dynamically here. And we actually have the compression stiffness set to 0, so they can get as close to the wall as they want to. They just can't get farther away than their initial rest length. And then we've turned on the sliding rate and set it to 1 with a scale by attribute of that sliding scale, which is on the target geometry. So it's just the way you would set it up as a SOP if you were doing just an initial or static setup at the beginning of the simulation, just doing this in a dynamic way. So in every other way, it's quite similar to to that previous example, although you'll notice breaking is off. So once we create these constraints, we're not breaking them. We're just letting them stay throughout the duration of the simulation. And then we do have, as usual, this keep unique within output group set here. So all that means is a given point, once it gets an attached constraint on it, it won't get any more due to this stop. It'll be limited to just one constraint per point. So if you're interested in that other file, it's along with that advanced Vellum workflow. You can get it from that masterclass. But this is a very similar setup using dynamic constraints, just in this case with sliding attached constraints. Finally, I'd like to talk about the new triangle and tetrahedral stretch constraints in Houdini 18. And these are as rigid as possible constraints, or ARAP constraints. That's a new type of constraint that ignores the rotations on like a triangle or tetrahedron while minimizing any stretch and shear. And that ends up causing elastic behavior. So basically behavior that will try to move the triangle or tetrahedron back to its original shape. So this is a new constraint that's actually on the shape of the entire element, the entire triangle or tet, versus just adding springs along the edges. And so that means previously to Houdini 18, if we took a triangle mesh or a tetrahedral mesh that was the result of solid conform or something like that, the only way we could constrain that shape or those elements to retain their shape is just to put springs along the edges of each triangle or tetrahedron or distance constraints. So this works okay until you get into extreme deformation, so extreme compression or stretching. And then it just starts to become very obvious that the only constraints are along the edges, not on the entire shape. And we'll see some examples of that. So for these to work, they need to encode the original rest shape of the element. And so for tets, that's in a 3x3 rest matrix attribute that you'll see on these constraints, or for triangles, a 2x2 rest vector attribute. This is particularly useful for organic material and anything that needs to naturally stretch or compress. It just gives much smoother behavior than when we would just use the edge springs that we had to use in previous versions. All of the new tetrahedral softbody shelf tools and network tools now use tetrahedral stretch as their constraint type, just because it really does work better. It's also an option to use these types of constraints for cloth. So for cloth, you can use either distance along edges, which is the previous approach, or you can use the triangle stretch constraints. And it turns out that at very high resolutions, even though the triangle stretch constraints are a bit more expensive, they actually converge a little bit faster in terms of just the number of iterations you need. So it can actually be effective to use these. And you get a little bit just, again, when the cloth does stretch, it just does it in a bit smoother way. And again, we'll see some examples. And finally, these types of constraints work quite well with plasticity, which again is the idea that a soft body might deform to a new shape. It might get squished by a collision object, say, and it'll actually move to where its current shape, it'll keep that shape. It'll keep that sort of squished shape. And that's generally referred to as plastic flow. And so it just turns out that, again, doing plastic deformation of the entire shape rather than just the springs along the edges just generally works better and gives a bit more stable and smoother plastic deformation. So we're going to jump into Houdini and see how this works. So now let's look at how these constraints work within the context of Houdini. And I'm going to start off by showing an incredibly simple example where it's creating a single tetrahedron here, and we're applying these new types of constraints. So this is the tetrahedral stretch constraint, which is the one that's one of the new ARAP constraints that's new in Houdini 18. And then in our solver, we have turned off gravity and we've turned off collisions. So there's just a tet just kind of floating in space. And if we hit play, not surprisingly, nothing happens. So we're setting up the constraint here. And if we look at what's coming out of there, you can see there's a single constraint. So there's one constraint per tetrahedron, and it's got this rest matrix attribute here, which basically is what's encoding the shape of this tetrahedron. And then after that, we have this transform in here where we can change the shape of the, or rotate or translate the tetrahedron. So if we move it, then of course, again, nothing really happens. If we rotate it, again, because as I was describing the constraint, we're essentially ignoring any rotations. We only want to worry about stretch and shear. So again, nothing happens. If we finally actually scale it and hit play, then we start to see that it's actually doing something. It's trying to restore its original shape. So I'm gonna actually get rid of the translations and rotations just so it's a little easier to see. So this is essentially it's like sort of a shape spring. So it's a spring that kind of wants it to go back to its original shape. And a couple of interesting things here, we can do things like turn the damping up, and so it'll restore its shape much slower, or we can make it a much stiffer sort of shape spring, so it'll go back to its original shape very quickly. So this is kind of the main function of the constraint, is just to restore the shape of the original tetrahedron. The other thing we can look at that's kind of interesting is if we are looking at this tetrahedron, we can look at its measured area. This is actually an intrinsic. So if we go to these intrinsic, there's a bunch of different things we can look at. So I'm sorry, not area, measured volume. We're looking at the measured volume of this tetrahedron. So if we look at as it starts out, it's about 0.0005. And now we've transformed it to start. So it's the volume is higher than that. And if we hit play, we can watch the volume of the tetrahedron. You notice it goes much smaller than the original volume, down up to 0.002 or even 1, and then back higher again. So this is not maintaining volume. It's trying to restore the shape of the tetrahedron, but it's not restoring the volume of the tetrahedron. And in some cases, that's fine. Usually for organic materials, you want the shape to be kind of not that stiff, kind of squishy, but you want it to retain its volume. So as the object compresses, it might bulge out around the middles, for instance, or if you're pulling it apart, it's going to collapse in the middle. So there's this option here to preserve volume here. And what this does is essentially apply an additional constraint on top of the ARAP constraint that is a tetrahedral volume constraint. And we have that kind of constraint actually to write here, this tetrahedral volume, and we used it in the past along with the spring edges to create soft bodies, but now it's built into this constraint so that when we hit play, you'll actually see that now these top points are going up to allow the tetrahedron to preserve its volume. So if we look at the measured volume during the sim, it's going to go back to around that original value and stay there. So this is, again, just generally you're going to want that on for any sort of organic object. Once things, if for example, you're doing something very stiff, and actually we'll look at an example of that, you may not care as much about preserving volume because it's not deforming much in the first place. And so then just to compare to our distance along edges, so this is what we did before. And so now we've actually, if we look at the constraints, we've actually got, we've got a bunch of them. We've got one for each edge. So we've got 1, 2, 3, 4, 5, 6. So we've got 6 for one constraint for each edge. So you would think that maybe the tetrahedron one is much faster because there's only one constraint versus 6. And that's sort of true in that you can actually get away with fewer iterations because there's a constraint on the entire shape. It's actually usually stiffer than creating these springs. But the spring constraint is so incredibly simple, the distance constraint, relative to the complexity of the ARAP constraint. It's a little bit of a wash, but you should definitely still be using the ARAP constraint for soft bodies. And then another thing that's kind of interesting is if we invert this, so you can see that this is inverted because we're now looking at the backs of these polygons. That's why they've turned this dark gray. If we go back to our tetrahedral stretch, it will actually restore itself, because it essentially understands inversions, and it will work to uninvert itself even if preserved volume is off. Whereas if we do the distance along edges, all it's doing is restoring the length of these edges, so it doesn't know anything about the tetrahedron. It doesn't know that it's inverted, so there's nothing that is in the shape part of the constraint that's trying to keep it from inverting, which as you start to have, again, extreme compressions or expansion like stretching, it can really start to become an issue. So let's look at a couple of examples of that. So here is just a solid box that we've turned into a bunch of tetrahedra with solid conform, and the target animation of this, we're just going to scale it. We're basically just going to stretch this. We've got some pins on each side here. So if we go down to the solid rings again, I think we have gravity here, but probably not collisions. And we're doing let's actually turn this off for a second. So we're doing just the springs along edges here, the distance along edges. That's what this constraint is. And we hit start. Let's get rid of that. So we can see here that this is kind of the problem. We've got all of these edges that are kind of inverting and they're kind of falling in on themselves. We have collisions turned off here, so there's nothing kind of stopping self-collisions from happening. And it's just kind of this ugly mess because the constraints don't know anything about the shape of the tetrahedra. All it's trying to do is keep these little springs along the length of it working, and it just can't do enough and can't do it smoothly enough to get a good result here. Now, things get better if we turn on that tetrahedral volume constraint that I was describing. So this is definitely better. It's still pretty noisy just for the same reason. You've got these edges which are trying to constrain the shape, and just adding a lot of noise in there just because the edges are, some will get extremely stretched and some will not, and so it gets just kind of very bumpy. And so the other way of doing this is with the tetrahedral stretch. And so we'll start off with preserve volume off. And if we hit play, you'll see we actually get this very smooth stretching because all it's doing is stretching along the length of these tetrahedra, and it's just expanding the shape of it. And so there's some elastic force here that's, it's getting sort of, you can see it kind of restoring itself. Looks like a rubber band kind of strung tight. But you notice that there's no compression along the middle as this object is stretched out. So it's what's called sometimes the Poisson effect. So it's the idea that as you stretch something out, it should sort of squeeze together in the middle, and as you compress it together, it should stretch out or bulge out. And that's because we have no volume preservation on. So if we turn that on, then you'll see we get that that sort of collapse or stretching, squeezing in the middle here. And so if we want to see this subdivided, which can actually be kind of a good way to look at this as organic material again. And just as an aside, if you want to subdivide something, you need to do this convert tets if you want to subdivide a bunch of tetrahedra, because subdivide won't work on the tetrahedra, but if you do convert tets, what it'll do is just convert everything to this back to the surface triangles. So that's what we're seeing here, is just the surface triangles, which we can then subdivide. And so you can see this looks like a pretty good organic material here. And you can see the same effect on triangles. So here we've got a kind of similar setup. We've got just a small patch here. And again, the target animation is just to stretch it out. And if we just do distance along edges, which is how like cloth works, for instance, is by just putting a distance constraint on each one of these edges of the triangles and solve that, then we'll see we get, oops, I'm sorry, I'm doing the other one. There, this is the distance along edges. So you see it's kind of a mess. It kind of collapses in the middle, and these edges all kind of fall in on themselves, and it just really doesn't look very good. And you get some inverted triangles, and things are just ugly. If we switch to the triangle stretch, so that's what this is, this triangle stretch here, you'll see we get this nice smooth stretching out of each triangle, because again, it's constraining the entire shape. Now, in this case, we don't have a preserved volume. In this case, it would be preserved area. And that's mostly because it's difficult to keep track of whether a triangle is inverted or not. So you don't get that effect of it squeezing in the middle there. For a lot of organic material that needs to stretch out over like skin or something like that needs to stretch over a collision object, it's generally not much of a problem, but it's just something to be aware of. You won't get that effect if you're looking for it, just like stretching an individual patch like this. And then finally, this is a setup of just sort of high-res cloth draping over an object here. And I've obviously already cast it out. It's not sitting that fast. And so this is, there's a stretch type here now when you use the cloth constraint type. And it's just whether you want to use distance along edges or triangle stretch. So this is the triangle stretch constraint. And one thing you'll also notice if you've done some draping in Vellum, this is actually settling down really quickly, which is good. There's also this new velocity damping in Houdini 18, which is a pretty brute force approach to just scaling down velocity. But it's quite effective in getting rid of just sort of noise that sometimes you might see some sort of bouncing in here. So you can either set this or even just animate it up if you want things to slow down. So the difference between this and using the distance along edges, I've got some flip books here. So this is what we're looking at. This is the triangle stretch. This is the distance along edges, and you can see there's a little extra. Everything's kind of moved to the right here with the distance along edges, just because there's a little more stretching. Not a lot, but a little bit. And if we actually look at this, So this is visualizing the area, the change in area of each triangle over the time of the simulation. So there's a bit of stretching, obviously, in both of them, but it's kind of noisy. There's like these kind of splotchy stuff, and that basically just means that the edges are getting stretched sort of inconsistently. And so the stretching that does occur doesn't look particularly good. And so there's still some stretching, obviously, in the triangle stretch constraint, but it's just much smoother because we're, again, constraining the entire shape of the triangle. So it ends up just looking a lot smoother in the simulation. So the only downside, well, one of the downsides to the triangle stretch is that all of these, actually they're gone here. So, but there's some anisotropic settings for cloth, and those basically go away if you use triangle stretch, because what they're basically doing is scaling the stiffness of the edges that correspond to or go against the direction of the UVs, and we don't have support for that in the triangle stretch constraint. So if you have any sort of using any of that sort of warp weft settings, then you need to stick with the distance long edges. Otherwise, the triangle stretch can be interesting as you move to higher res cloth. So that's the basics of how these constraints work, and I wanted to just show how they work now in the shelf tools. Now I wanted to go through how you might use these ARAP constraints, particularly the tetrahedral stretch constraint, within the context of the Houdini shelf tools. So I'm just going to put down a squab geometry here and make it a little bit smaller, and go to the Vellum tool, shelf tool, and choose tetrahedral softbody. And so this is going to set up not only the simulation, but also a deformation network. So something that takes the original model and turns it into tetrahedra and then point deforms the original model. So you can see here, now we're in the dot network, and we obviously don't have enough resolution here. So we're going to go back to look at this setup. And so what it does is it takes that geometry, it poly reduces it, and then remeshes it, and then solid conforms it. Let's turn off the material for just a second. And this is just not high enough resolution. So and this, you don't necessarily need to poly reduce it, but it's just sort of a convenient way to dial in resolution. The remesh is the one that really makes a big difference here. We're going to be using a uniform edge length. You can use adaptive with this. You just need to be kind of careful about all these sort of bits around here that can cause self collisions, even with the calculate uniform thickness or even the calculate varying. It can still cause some problems. So if you're using adaptivity on the remesh, I would recommend not using too much of it. The more uniform your tetrahedra can be, it's just generally better. But so once we have a better looking in terms of resolution mesh, we can, so what's happening here is the original geometry is being fed into the point deform, and then we're feeding both the non-simulated rest geometry here and then the result of the simulation as well. So it's going to deform this, but we don't have any collisions yet. So let's add a ground plane. And we'll go back to our squab, turn on materials again, play. So what will happen is just the simulation is the object's falling down. Obviously, it's kind of squishing like a nice soft body, and then we're deforming the original mesh to match that. So this is a pretty, if you've ever done any sort of soft body FEM stuff, Vellum, tetrahedral soft body in previous versions, this is a pretty common workflow. So you could do the same thing by using the network tool here, going configure tetrahedral soft body, and that puts down both the solid conform and the tetrahedral stretch. So it's sort of this part of it, and then you could go to like a Vellum solver here. Whoops, sorry, I just did the same thing. And hook these up, and oops, let's put the remesh, and you basically get the same setup. So either way, it doesn't necessarily matter. Maybe we'll just work from here. So in this case, we'd be using this, the result of this, and we'd want to turn on our ground plane and again move it down. So we're doing the same thing. We're just doing it all now within the network. You could do it, either way is totally fine, whichever way you're more comfortable working. So one thing that is nice about these tetrahedral stretch constraints, especially when you're using them as soft bodies, they're fairly efficient. So you can usually use a few more iteration. I mean, a few fewer iterations. If we wanted to make this a little stiffer, we could go maybe to here, just so it doesn't. Yeah, so it just has a little bit less compression and bounces up just a little bit, holds its shape a little bit better. And we can do something like, let's add some pins here. So we're going to change this to pin to target and select just a few points at the top. Okay, so now we've just sort of pinned the head of the squab up here, so we get some sort of slightly different behavior. And again, you can see the difference. Like if I go and you can see that as the head, I guess that's the head of the squab, stretches, it has that narrows here as so it can preserve volume basically. And so if we go turn that off, you'll see that now it just stretches and it doesn't preserve volume. So it actually doesn't look too bad otherwise, just as a soft body. If you're looking hard, you might notice that. So, and it is a little faster, a little less expensive to turn off, preserve volume. So it's really kind of just up to you whether which look you're going for. The other selection here, use linear model, is a different way of solving the constraints. Basically, it linearizes the constraints. It doesn't look as good when you're doing sort of very soft constraints that want to stretch or deform a lot. But if you do something like you basically say, I want an extremely stiff tetrahedral soft body, then actually turning this on is a pretty good idea because it will converge faster for high stiffness. So you can see now we get very little stretching or deformation of the object relative to what we were doing before. And in fact, we're safe leaving preserved volume off here because the head part of it isn't really deforming at all, really isn't really stretching. So the fact that it doesn't preserve volume is not all that noticeable because the shape constraint is so strong in the first place. And then if you really want to make this stiffer, though, you might do something like increase the substeps or something like that. And so if we let it bounce, you can see it's much stiffer here. And it's not quite a rigid body because you still got some sort of flapping in the tail and stuff and then the tentacles, but it's just a lot stiffer. So just depending on which look you're going for, sort of determines whether or not you'll use this linear model. If you're going for organic material, usually you want it off. It's just if you want something much stiffer than that. So anyway, this is a really quick overview of how you would use this setup within the context of Houdini and the shelf tools. I wanted to show a quick example of using the tetrahedral stretch constraints with plasticity in Houdini 18, just because they work particularly well. This is a real simple example where we've just got a soft body torus falling down on a collision object and then on the ground. So nothing much going on here, but we're visualizing stretch distance. And in this context, what stretch distance means is basically how much has each tetrahedron deviated from its original rest shape. And so we can actually turn on plasticity on these constraints and have it work on the stretch constraints, the tetrahedral stretch constraints. And we want to have this threshold here, and this isn't a percentage of change, it's just an overall change as compared to like what we're visualizing here. Our rate says we want to deform fairly quickly. So basically the rest shape, we want it to deform towards the current shape quite quickly, and we want the constraints to get harder as they do that, or stiffer as they do that. So it'll be like something like clay, where as you sort of compress it and you squish it, it sort of gets stiffer in that new configuration. So if we turn that on, and we're going to actually also switch to visualizing plastic flow. So that's just a measure of how much plastic deformation has actually happened. And let's look at the constraints here. So if we sort this by plastic flow, we can actually see that as the deformation is happening, so as the plastic flow is changing, the rest matrix is changing. That basically means the shape that each tetrahedron represents is changing. The rest length is staying the same. That actually encodes the volume of the tetrahedron. So we're preserving the volume, and that's what the preserved volume constraint is looking at. And the stiffness is increasing, and that's because of that hardening setting. So you end up getting, and you can see as you end up getting something that looks like maybe clay or something like that, where the shape of it changes, it retains its volume, and it gets stiffer along the part that has been plastically deformed. And so I've cached one that just has a lot more objects in it. You can see because they're kind of squishing each other, I had to increase the substeps a lot to get better collisions, but you can see there's a lot more plastic flow here. You get some pretty extreme deformations, but things stay pretty much nice and stable. I also did the same thing, but with preserve volume turned off just to see it. And you'll see that they actually kind of, when they get squished, they don't preserve volume, so they actually get a fair bit smaller. So if you just compare like sort of the size of these sets of objects, these are obviously much bigger because they preserve volume. They sort of expanded out, squished out a little bit more under the collisions versus these ones. So anyway, that's just a quick example of plasticity when using the tetrahedral stretch constraints. I wanted to show another quick example of using these ARAP constraints to get some nice organic looking behavior. So here we've just got a box that we've remeshed and made to fairly high resolution tetrahedral solid here. And then we add the tetrahedral stretch constraints, not very stiff at all. And then we're also, when we do the solid conform, we're creating that surface triangles group. So we're keeping triangles on all of these tetrahedra that are on the surface. And we're applying a triangle stretch constraint to that. So this is a bit like having sort of big organic mass inside with some sort of membrane like skin or something on the outside that's pretty stretchy, so pretty low stiffness. And then we're actually adding bend stiffness across all those triangles. So this bend across triangles is the same constraint that's used in cloth, but here we're just applying it to the outer triangles. And then we're pinning the ends up here. So if we watch the results of that, and again, obviously this is pre-cached, but you can see it gets some nice wrinkling behavior here, just from those outer triangle stretch constraints that are kind of acting like that stretchable membrane. And how much wrinkling you get is actually controlled mostly by this bend strength here. And then if you want, you can do things like do that same thing we did before, where we converted back to tets and subdivide, or you could point deform. There's a few different ways to do it. Actually, point deforming might even be quicker, but sort of some interesting looks here. And so I just did a couple of movies or flipbooks here. This is with no bend stiffness at all. So you see you get a very wrinkly kind of behavior here with lots of wrinkles showing up sort of all across the body, and not even just where it's bending so much. And then this is with sort of a medium bend stiffness. And you see the wrinkles are mostly relegated to just this kind of high bending area here. Anyway, so and obviously all these files are going to be included with this masterclass, but just kind of an interesting little example of using the two different ARAP constraints. I wanted to go in a little more technical detail about the tetrahedral ARAP constraints, and not because you necessarily need to know any of this. I just think it's kind of interesting, and in particular, it shows some output from the solver that we can use to do some kind of stupid Houdini tricks that lead to some interesting emergent behavior on soft bodies, which I'll show a couple of examples of. So as I've described, these ARAP constraints encode the rest shape of the tetrahedron, and while we're solving, we can combine it with the current shape of the tetrahedron, and we form something called a deformation gradient that we can call F. And all that is a mapping from the rest space to the deformed space. We want to find the rotational part of that. And so all that means is if all the tetrahedron has done is rotate, then there's nothing to do. There's no elastic forces. So we want to find the best rotation from the rest state tetrahedron to the current state tetrahedron. And there's a couple of ways of doing that. There's something called polar decomp, which is a function in Vex. But the solver actually does that internally. Then the constraint solver does it. And it actually stores that current rotation as a quaternion in the rest vector attribute. And we're going to use that in this demo to do some interesting tricks, some interesting behavior. Once we have that mapping, that F mapping and the rotation, which is an R, we just subtract one from the other and minimize that. So that's just a way of saying disregard all the rotations and minimize what's left over, which is the stretch and the shear. Again, don't necessarily need to know that, but the interesting part here is that we've got that rotation. At any point in the solve, we've got a rotation for the tetrahedron. There's no volume preservation here without that additional volume constraint as we talked about. And this model in general is not really that accurate a description of elastic behavior. It's not as accurate as something like the Neo-Hookean, which is in the Houdini 18 FEM solver, but it can be solved with XPBD. It's a simple enough model that it can be solved with XPBD. And as you've seen, you can get some really nice organic behavior even with this simpler model. So that's why we've implemented it in Vellum. If you need super accurate elastic behavior, then you probably need to look at something like the FEM solver. But for a large subset of the problems, you can get some pretty good results with Vellum and these types of constraints. So now I want to show a couple of examples of using that rotation, that R that we figured out from each tetrahedron to get some kind of fun behavior. Now I wanted to show that demo of using that rotational part of the ARAP constraints to drive some interesting behavior on a tetrahedral softbody. And so this is a demo that's called the box of snakes, which is probably going to become obvious why. But all we're doing is creating a bunch of little tetrahedral boxes, and we're creating this material W attribute. And if you've used the tetrahedral fiber constraints at all, you'll know that's just a vector in rest space that's pointing in kind of the main direction of the tetrahedron. It could be anything you want, but in this case, we're just doing it along the body of the of this kind of box here. And so if we visualize that here, you can see it's just pointing along here. And we're going to ultimately create a whole bunch of these. So we're going to want to bypass that. And you can see in each case, in rest space, the material W is pointing along the snake. And the one thing you need to be careful about here, by the way, is make sure you set this to vector so that when these copies are rotating things, they will actually rotate the vectors. If you leave this as float, they won't get rotated. So you need to make sure that if you're copying this workflow to always use a vector there. So then we basically are just creating heads for them. Actually, for the moment, let's bypass these. So we're only working with one. And create the tetrahedral stretch constraint, and then go into the Vellum solver. So a very straightforward setup. And then the only interesting thing we're doing here is in the Vellum solver. So this is just the Vellum solver SOP. We've got this pop wind. So this is a regular pop wind. There's a couple of interesting things here, though. As of Houdini 18, there's now this inputs tab. So it used to be that it could be kind of difficult to go grab different inputs from within a pop, which is mostly useful if you're using Vexpression. So if you want to write a little bit of Vex code to give yourself sort of a custom wind force, and you needed to look at other pieces of geometry than just the particles to calculate that, it could be kind of difficult prior to Houdini 18. So now we have this inputs tab, so you can actually bind other pieces of data or SOPs or any sort of thing to get that data to calculate from. So in this case, we're just grabbing the constraint geometry. So this is the constraints primitives that during the solve. So we'll be able to look up interesting values from that. And actually, let's look at what that is. So the Vellum, and again, if you see the advanced Vellum workflow masterclass, I go over that in some great detail there. So this is the constraint geometry, and these are the primitives. So these ARAP, there's some stuff on the front and on the back of it, but there's ARAP here. So these are the ARAP constraints. So what we're doing is we want to create a wind vector along this object, basically always pointing along the direction of the snake of this box. And we want to do that no matter what direction it's pointing. So whatever direction this snake and these tetrahedra have oriented themselves to, we want to always be moving along this direction. So even if it curls up into like a loop, we want it to always be moving this way. And to do that, we can actually use that rotation that's been extracted by the solver for each one of these tetrahedra. So each one of these tetrahedra is going to have its own orientation. And so what we can do is, this is what this code does. I'm going to just describe it really quickly, and you can look at the example later. But essentially, it's grabbing all of the point primitives for the current point from that constraint geometry. So it's basically saying, give me all the constraints that are going to be working on this particular point. And then I'm going to go through all of them and look for, and this is a function that's in this PBD constraints file that's included with Houdini, and just say, is it a tetrahedral ARAP constraint? And if so, then I want to look at that and use it. So once we've found it, all we're doing is getting that quaternion rest vector that I described from it. And then we're creating a local velocity direction using that material W. So we're rotating the material W into the current space. And then we're making that the wind direction. And so it's probably easier if we visualize this. So if we visualize the result of doing that, and here we created that, we did this set point attribute. So we created this little local V direction, which is the rotated material W in every case. If we view that as we simulate, that's what we're seeing here, these vectors that they're being rotated. And you can't really tell until it hits the wall here. But once it hits the wall and starts kind of wiggling around, you can see that that wind is always getting reoriented to move along the direction of the body of the snake. So that's why you get this kind of weird, interesting, curling back and forth behavior, because it's trying to always push forward and it's fighting against these collisions. And that kind of gets more interesting if we have more of these. So if we do this, we'll get a bunch of different, and you can see again that they all start out or aligned along the direction of the snake. And even this guy that's sort of curling up, again, we're using that rotation that the solver is figuring out for the tetrahedron to rotate into a local wind space. So we end up with this kind of cool, interesting behavior. And so, and I've saved out having even a few more of these. Cast it out. Sorry, here. Load from disk. So this is why it's obviously called the box of snakes, because that's what it kind of looks like. So you've got all this kind of interesting behavior coming out, and it's a very, that code looks a little bit complicated, but there's very little of it. And it's actually, we're not adding any noise here. We're not adding any randomness at all. All we're doing is telling each snake and each part of the snake, move forward as fast as you can. Well, not as fast as you can, up to the speed of the wind, basically. And we get all this kind of interesting behavior from that. I'm going to show this really quickly. Again, you don't really need to know this, but this is basically doing the same thing, but actually combining the matrices that we talked about in Vex code and then using that polar decomposition to figure out the same thing. It's more complicated, it's slower, and you already have it from this quaternion, so it's probably not worth doing, but I just wanted to include that code if anybody was particularly interested in how it worked. This sort of combination of the rest matrix and the current matrix of what's going on in the solver, but again, you shouldn't really have to worry about that. So one more example of that is just the same idea, but we're gonna, let's say we do it with, instead of that box, we're gonna do it with just sort of a subdivided box as a collision object. And then we're going to do one more thing, which is we're going to basically do the exact same thing, but we're going to add dynamic attach constraints. So once the snakes fall down on the object, we're adding these dynamic attachments, and then they're basically able to sort of crawl under the underside of this object as well as just across the top of it, which again is just kind of cool, interesting behavior. And so if we look at the cashed out version of that, you get one that just his sort of the tail, his tail gets stuck and he kind of tries feverishly to get off, but he can't. And these guys kind of cruise around and interact with each other and slide across the surface of this object, which is just kind of, again, just kind of a fun look. So this is exactly the same, just going into the solver. This is exactly the same pop wind that we looked at before, and then we're just adding a dynamic attach constraint for the first 50 frames, like we were talking about previously in the dynamic attach demo. And then just to show a slightly more professional version of this, we've got this something that one of our internal TDs did, which is the same kind of idea, but using it for just a single sort of tentacle object. And this has actually got some rest geometry that's just kind of doing this kind of contraction expansion thing, kind of looking like a worm or a tentacle or something. And then the setup here, it actually uses the Vellum rest blend to bring that rest shape into the simulation. It again has some sliding based on the noise that's kind of moving along here. If we go back and look at this, so this is where the sliding is happening, where the contraction is happening. So again, you just get some kind of really interesting emergent behavior from a relatively simple setup. Anyway, that is all I have to show for this masterclass. I hope you've enjoyed it and learned some interesting things that you can do in Vellum and Houdini 18. Thank you very much.